Okay, this is projectile motion example number 1. What we've got is a cannon on top of a cliff. The cannon is going to fire horizontally with a muzzle velocity of v, which equals 100 meters per second. The height of the cliff h is equal to 50 meters, and my job here is to find the horizontal distance that the shell travels after firing. So I'm effectively finding S. I'm going to call this SX, just to make sure that I can keep that separate in my calculations. Okay, so I know that SX, I'm going to try and keep the colours separate here as well, so you can keep track of what I'm doing. So SX is going to be in green, and I know that that is going to be equal to VX, which is going to be in blue, times by the flight time. So I'm going to call that T subscript F. I'm going to do all of the working for that one in red. Okay, so VX is really easy in this example, because it's fired exactly horizontally, and I'm taking air resistance to be negligible, which is what we do in these questions. I know that VX is going to equal 100 meters per second. Okay, so that's half of my equation built already. So to find the thing that I want, I need Vx and Tf. I already am given Vx in the question. So now I just need to think about finding Tf. So Tf. Every single time I do something like this, I'm going to use suvat. So I'm going to write out one after the other like this, and I'm going to see what I've got and what I need. So I'm after a time. That's the thing that I want. So I'm going to put a little star by that. I'm going to start at the top. S. Well, in this case, we're talking about the vertical distance that it's going to drop. That's how I find flight time in this, because we know that something travelling horizontally has nothing to do with its vertical velocity. We know that something thrown horizontally and being dropped from the same height spend the exact same amount of time in the air. So S here is just H. It's the same as either firing it from the cannon or dropping it from the top of the cliff. So I can use some convenient points in my projectile motion equations to solve this by looking at the drop time. So S is going to be H, which equals 50 meters. U is going to be UY, the initial velocity in Y, and that's a really convenient number, 0 meters per second. It's fired exactly horizontally at the beginning. It has 0 velocity in the Y direction. Now V, that would be the final velocity that it hits when it gets to the bottom. Now I don't know that, so I'm just going to put a line across that. And A, remember we are always given A by virtue of it being little g. So we know that every single time. That is one that we are never explicitly given in a question, but we always have. Right, and then I'm going to look at the variables that I've got and the one that I want, S, U, A and T. That leads me to the equation S equals ut plus a half at squared. This is really convenient because u is 0, so that thing goes to 0. So I can say therefore S equals 1/2 at squared. I can then say that 2s equals at squared. I can then say that 2s over a equals t squared, and therefore t equals the root of 2s over a. And I'm going to take this and I'm going to say that TF here is equal to 2h over little g all rooted. This equation, s becomes h, as I've said, and a becomes little g. So now I have two things that I can use to get to the end. So I'm going to do all of this in green because this is now finding Sx. So I know that Sx equals Vxtf, which equals 100 times by root 2h over g. Now that equals 100 root 200 over g, and that gives me something that I can put directly into my calculator. So I'm going to do 100, then I can push the square root sign followed by the fraction sign, and then I can put 200, and because I've got this fancy calculator I can put my value of little g straight in as a constant. Then if I press equals, I get 450 metres. That's to two significant figures. I can double underline that. So that's how you find the horizontal distance. I can also do something quite interesting with this little graph up here. I can graph my values of Vx and Vy just to have a look at them to see what they look like over the time that they're in the air. So I know that Vx, if I do this one in blue, basically does that, where that is Tf and that is 100 meters per second. Now I can say that it does a flat velocity of 100 meters per second up until the point Tf when it hits the floor and stops dead. So that's the graph of Vx. So I can say that is Vx. Now for Vy, I'm going to have to be a little bit cleverer. So I know that Vy in the first place starts at 0. So that's going to be at the origin. And I already worked out the flight time for this to be about something like 4.5 seconds. So if we take the acceleration, g, to be about 10, that means it's going to be doing probably about 45 meters per second vertically. So that's a little over halfway, a little under halfway up this side. And I know that on my VT graphs, acceleration is given by the gradient. I know gradient and acceleration are constant here, so I can draw a straight line. And that also becomes 0 at Tf. So that one will be Vy. Just an extra little bit of skill that we can use there to do that.